190. Steve Wheeler really apologizes, but he has to be in Paris this week for a conference. So everybody feels sorry for Steve in Paris today. I'll here let a few people sit down. Today we have Bill Starr and Gary Dahl from A&E, is what it's lovingly known on campus, or architects and engineers for the campus. I'm going to let them do their sort of own introductions and setup here. And welcome, Bill and Gary.
I'm Gary Dahl. I'm Director of Project Management for A&E, although we just recently changed our name to Design and Construction Management.
Ooh.
Same office.
So
So our office is responsible for the design and construction of nearly all the major projects on campus. We currently have about $1 billion worth of projects in some phase of either programming, design, construction, or warranty phase. And we do roughly about $200 million a year of projects. So a lot of buildings.
And I'm Bill Starr. I'm a senior project manager. Worked on several projects, some of the early ones that looked at LEED, as well as quite a few that are going on now, and kind of working on some of the campus efforts where sort of the buildings interface with other campus issues. So we've got a lot to cover here today, and we're going to have to move pretty quickly on a lot of different issues. But I do want to encourage questions. We're going to try to get some discussion time at the end to really talk about some of these bigger issues. But because obviously the buildings have impacts and also are a pretty daily part of our lives. So first I wanted to talk a little bit about why we're talking about buildings today as part of sustainability. And I'm sure many of you are familiar with some of these metrics. Just a huge sector of resources go into both constructing buildings and operating them. This is a pie chart that was, this is actually the sectors that are broken out by the Department of Energy. So you can see they don't actually describe a building category. It's broken into residential and commercial and industry and transportation. Those are their four main factors where they show all the energy in the U.S. going to. This upper chart is actually an effort to try to take both the commercial sector and the residential part that relates to buildings, as well as the industrial capacity that actually makes building materials, and roll them up into sort of a global number of almost 50% for the energy sectors. So that's sort of at a general scale. When we talk about CO2 emissions, they're also a huge chunk. Now this is from Berkeley's report that Berkeley did. Ours is somewhat similar, but you can see there's the total kind of campus, there's the total emissions that have to have both life cycle emissions that have to do with long-term construction and demolition of things, and then there's the operating or the non-life cycle emissions that are the ones in this pie. So you can see electricity, steam, natural gas, and refrigerant emissions. If you sum those up, it's over 45% of the picture. Right now, the emissions, I think, of what's been counted so far, it's over 90%. So once you take that and then look at the construction impacts, an additional 20%, at least in this case, and I think that's probably pretty close to our campus, it's a huge chunk of the CO2 impact that the campus has. So just to look at that, here's a list of the actual energy and emissions associated with new building. And so you can see the one that most people kind of focus on is this energy for operating the building, actually running the lights and the power and the HVAC systems. But there's all these other areas that come up in the lifespan of that building that can be significant. And I'm going to talk about two examples, both the embodied energy in the beginning and then operating energy. So actually to do the operating energy first, since most people are more familiar with that, these are just the results of doing the energy analysis on a large lab building, the VetNet 3B project, which I'll talk a little bit about later. And the baseline case is essentially, if you built it just to code, what energy would you use? And we've got the CO2 conversions, get a sense of the tons. If I recall correctly, the total campus emissions of CO2 equivalent right now, I think is It's 200, 250.
Yeah.
So this has both gas and electricity. So you can see, doing all these energy efficiency measures, and we applied a lot to this building, saved or reduced it from the baseline about 850 tons, but you still end up with 600, almost 700 tons that you added to the campus, even after all that effort. So it's still adding on to the amount that we have to essentially offset. To one that's a little less known is looking at the actual energy that goes into the materials that go into the building itself. So these are some calculations I did on the materials, and there's a Rosenfeld rule. Art Rosenfeld of the Energy Commission has generally done a lot of calculations showing that in any product, typically 10% of the cost is actually energy on average if you're looking at a product. So this was applying that as well as some other metrics to come up. So it's somewhere between 8,000 and 19,000 tons for that 3D project. So you can see it's compared to the annual energy, which was like 693. It's a substantial amount larger than just the annual energy emissions. So what's interesting is that if the building was not energy efficient, it would be a smaller proportion, or it would be only 5 years worth of the energy use. But because we made the building efficient, it's actually a larger piece relatively. This is a graph showing costs associated with the building over the course of its lifespan. And it's diagrammatic and obviously kind of regularized. But it's just to illustrate that when it goes into the building, energy costs, there's a huge spike kind of during construction when all the materials go in and all the materials are supplied for that building. Then the operating energy kind of, reality, this would fluctuate. And then there's maintenance costs, which is the purple, but then not to lose sight of the fact that we want to support the functions of the people that are in those buildings and their productivity, because the relative costs of all the salaries and the function of those people is actually much bigger than both the operating maintenance costs as well as the energy. So you want to make those environments supportive of the people in them. The good news is that generally the effort toward making greener buildings has improved buildings in terms of general occupant satisfaction. And this is from the Center for the Built Environment at Berkeley, where they went and looked at a bunch of different buildings that were either classified as green buildings versus general buildings that they had done occupant surveys on. And the point to take here is that generally people were above neutral in most of the buildings, but the kind of median level for the base buildings that weren't designed to any kind of green standards was substantially lower than the ones that they're getting on average with the green buildings. So that's showing a good thing. What's interesting, just a couple side notes, is that acoustics is the only score that generally green buildings have performed less than standard buildings.
There have been a number of other studies that attempted to correlate things like occupant health, absenteeism, productivity, learning ability to the design of the building in terms of its ventilation rates, its lighting rates, and so on. So there are a number of studies that kind of all point in that direction.
And I was real excited to see this moved over here where we actually had a window and daylight versus being over in Wellman, I think, where it was originally scheduled, which I've done a lot of presentations on daylighting and the advantage of the health benefits of daylighting in completely closed off rooms. So just dealing with the scale of our campus, I put this in here just to try to give you a sense of, I think we all are aware this is a big operation, but it's a huge, we're a very land-rich campus, but even the central campus itself is over 900 acres. So it's a large amount of land. It's a huge number of buildings. You can see there, even in the central campus, we've got almost 600 buildings. And then the annual expenditures, there's $200 million. This is just slightly less than the med school's operating budget, which is substantially higher than almost any other unit on campus. And all the maintenance costs that are associated and the utility costs are in here as well. Actually, utility costs make up about half of that. So I'm using sort of energy and environmental impacts of CO2 somewhat synonymously as we talk through this, but this was a graph I prepared for the Focus the Nation event a while back, just looking at campus population growth, building area growth, and then projection and energy growth. And so the good news is that before we significantly had a significant policy on sustainability, the campus was already making some improvements or requirements for energy efficiency. So back in '96, the standards started requiring that new buildings perform 10% better than Title 24 of the Energy Code. And you can see it's actually dropped the line of how we're increasing. What's also significant is it's gone from the 1990 baseline, which is most of the policy is based on. We've almost added an equivalent amount of building area or building energy use in a very short time. So it's still a climbing line. And this gives you a rough sense of the reduction goals. There's a goal that by 2014 we need to be to a 2000 baseline, and by 2020 be to a 1990 baseline. Anybody have any questions on that? I'll hit this again.
That's university goals, not GSA or something from the state.
That's university goals, yeah.
And just to clarify, these baselines are buildings only. These are not including our fleet, our scope, our community,
Good point.
miles traveled, and research gases and all that.
Yeah, if you remember that pie chart, when you looked at those emissions, there was a substantial chunk that was transportation that this does not address.
One thing to note also is that California's Title 24 Energy Code is very aggressive. It's probably the most aggressive in the nation. And so we're actually doing pretty good relative to that baseline and relative to the nation.
Yeah, I was almost tempted to plot the Texas code up there, just to see it. We could claim so.
Okay, this chart just shows some of our recently completed buildings and how we are doing relative to energy.
No, you haven't.
Anyway, the baseline here is California's Title 24 Energy Code. It got reset in 2005 to become more aggressive, about 10 to 15% more aggressive in terms of efficiency. The red bar represents the region's policy in terms of what we are targeting. It was originally set at 10% better than Title 24, and then it has stepped down now. It's better than 20% better than Title 24, which in turn has been made more aggressive. The green bars represent individual projects, and as you can see, we have generally been hitting or exceeding our targets. These represent most of our major buildings in the last few years. And they're fairly representative of our projects. So I don't know how many of you are familiar with the Leadership in Energy and Environmental Design program. It's a national program to promote energy efficient and sustainable design in the built environment. The regions have adopted conformance to LEED as part of their sustainability policy. LEED basically gives you points for a variety of innovations and sustainable features. This represents kind of roughly the proportionate breakdown of how those points are obtained. Sustainable sites, water efficiency, energy efficiency, materials, which has to do largely with recycling and or VOC content, that sort of thing, and then indoor air quality. And then there are also a few points possible for innovation in a variety of areas. The points system have four levels: certified, silver, gold, and platinum. The current region's policy for all new buildings is to achieve a gold level of certification, with silver as the mandatory minimum. And so, which one did I hit?
Just the bottom arrow.
So this is a list of buildings that we have completed since that policy was adopted. At this point, we actually only have one building that's actually gone all the way through the process. It's the Tahoe Environmental Research Center. Bill will talk about that in more detail in a few minutes. We are currently preparing documentation for these three projects, two of them at gold, one at silver. And then we also are preparing documentation for self-certification for several other projects that were recently completed. The UC policy has allowed us to either go through the formal LEED certification process or self-certification process. It's pretty much the same in terms of the rigor and documentation. We are doing all new projects through the Green Building Council for formal certification, but we still have some legacy projects that we're self-certifying. This is a list of projects that are still in programming, design, or construction. We will talk about some of these in a couple minutes. As you can see, we have a range of platinum to silver. There's about 18 projects currently in the program. And then these are a few that are being self-certified. They're also in design or construction. Some of the projects don't neatly fit into the LEED U.S. Green Building Council program, so there's some unique aspects to working on a campus. The LEED program was essentially designed for standalone buildings built by a developer. There's some unique things about how we aggregate utilities and sites and so on that don't directly correlate to the LEED program. So sometimes we pull those out of the program and self-certify.
Yeah, question.
Sure. Just a quick question. When you go for the certification, does it include the furnishings that are brought into the building, or from your perspective, is it just the shell and the lighting and the energy use?
Yeah, it does not include the furnishings.
Okay.
Now, there is a existing buildings rating given by the Green Building Council as well, which I think does take into account.
But you can actually, under new construction, you can opt to count the furnishings if they're part of the project, but typically on capital projects, we don't have furnishing budgets. The departments that have handling that separately. So, but once you count it, you got to count it for everything. So you can't kind of just cherry pick. So you have to make that decision.
It's a fairly arduous process. The goals are very specific. There's a tremendous amount of research and documentation that's required for each of the points. This project is a project that is just now starting construction. It's the Brewery Winery Pilot Facility project. The project manager for that is here, actually, Julie Nola. Julie, do you want to talk a little bit?
No, Gary, you're doing great.
This is a project we're really proud of. It had fairly high sustainability aspirations from the beginning. We have been successful in getting a donor to fund, I think, $2-3 million additional cost to bring this building up to a LEED Platinum rating, which is the highest rating. Typically, we find that, just an aside on cost, we find that going to a silver rating or even a gold rating typically does not involve significant cost. It may involve some trade-offs between design features and maybe trading off some things that you wanted to do other things for sustainability features. But typically, there's not a significant cost to it. There's a fair amount of engineering cost and design cost, but in terms of the actual construction of the building, if it's done right, it doesn't necessarily cost more money to do a sustainable building or a more sustainable building. Once you go to the platinum level, it does start costing money. It's pretty hard to avoid that. There's some very aggressive energy efficiency goals, for example, that require additional equipment, solar panels, etc., to achieve those that high rating. One of the unique features of this project is that they are capturing rainwater and planning to use that initially, at least, for irrigating the landscape, and potentially in the future to actually use it for the processes going on inside the building. It's a fairly complicated thing, more complicated than you might think, to use rainwater in terms of how it has to be treated. There are a number of very strict regulatory requirements, especially if we're going to use it for what we hope to eventually use it for, which is food processing, and brewing, and winemaking.
And you want to try and not use a lot of energy, because that's the goal. You're trying not, to capture.
And that's a good point. A lot of sustainability goals actually conflict with each other. They involve trade-offs. For example, if you want to put in daylighting, that typically brings in more heat to the building. You then have to increase the air conditioning load to account for that heat. And so it's a constant assessment of what those trade-offs are, trying to get in that game. So this is the graduate school management, just recently completed. It is going for a gold rating as well. It involves some fairly innovative systems, at least for this area. One system we're using there is a ground source heat pump system to heat and cool the building using the stable temperature of the earth down below. We are also using a radiant heating and cooling system. So we're actually cooling the floor slabs and the ceilings in this building. People's perception of temperature is related as much to the radiant temperature as it is to the ambient temperature. So in a building like this where the surfaces are closer to where you want them, you can actually let the air temperature fluctuate a little higher and actually save energy by doing that. There are also some very innovative systems in terms of how the air is distributed through the building. We're using it's called a low velocity displacement system, where the air is introduced low as opposed to being blown down from ducts on top. They also use pretty extensive daylighting and drought-tolerant landscaping. This next project is the physical sciences building. This, I think, was, one of the things that's kind of interesting about lab buildings is that they're extremely energy intensive. They typically use 3 to 5 to 6 times as much energy per square foot as a building like this one uses. That's because of processes that go on inside the building, but also the need to have very, very high rates of ventilation to make sure that the toxic substances being used inside are not harming the occupants. So you have huge amounts of air that need to be cooled or heated depending on the time of the year, and then exhausted in one shot. It's not ever recycled, so it's just a huge energy hog. One of the things that we've been looking at is to challenge some of the assumptions about the design of labs. One of the assumptions that has been made over the years is how much energy is required to provide plug loads for all the equipment that go into labs. And the engineers like to be very conservative about that, because if they're conservative, then they never get a call saying we don't have enough power. Well, the downside of that is that the whole system is over-designed. It's not just the electrical systems that it's over-designed to meet that very high plug load that really isn't there, but also the HVAC system then has to be designed to cool all that electrical heat that's going into that building. It results in very inefficient buildings. So we've done some analysis of existing labs to try and determine how much we really do need, and try and lower that. And this chart here in the lower right here is an indication of how we've done that. This is the new law school addition going up under construction right now across from Rack Hall. It is targeting silver or possibly gold rating. This project kind of illustrates some of the things that we're trying to do in a number of projects with site remediation of stormwater, which is becoming more and more of both a regulatory issue as well as a sustainability issue. And Bill's going to show a better example maybe in the instructional facility project. This is our health and wellness center. Again, this is targeting right on that borderline between gold and silver, hopefully gold. You can see on this project that a lot of the points are gained by indoor air quality, which we thought was very important for this kind of facility. The points in that area are gained by doing things like using carpets and adhesives and building materials that have low off-gassing of toxic materials and formaldehyde, that sort of thing. This is the Oxford Dining Commons renovation project. This is a renovation project. It comes under the LEED Commercial Interiors program as opposed to the new building program. This one is targeting LEED silver rating. some of the interesting kind of tie-ins to this project is that in addition to some of the features of the building itself, they're also trying to make the dining program more sustainable in terms of locally produced foods and sustainability harvested foods. This is the Tercero Phase 3 housing project. And this project is targeting exceeding Title 24 by 25%. It's using solar heating for the domestic hot water system, for showers and sinks and that sort of thing. It uses a lot of the features that we use in all of our buildings: high performance glazing, sun shading, proper orientation of windows to minimize solar gain. They're also doing stormwater capture and treatment on site.
So this is the vet and instructional facility, also Valley Hall. It's got renamed as Valley Hall out in the Health Sciences District. In this building we have a mixed mode ventilation system to reduce energy use and actually, I think, make a more pleasant environment in the central commons. So there's a two-story public space in the central commons that sort of acts as a surge space between classes, so students move in and out of it. And surrounding that, we've got operable windows and actually operable louvers that are controlled by the mechanical system, so that when the air temperature is within a certain comfort range, like today, if you go out there, those louvers would be open, and the air would be flowing in through those louvers and out just a passively ventilated stack at the top. So what's interesting there is you can every once in a while you're out there and it feels fine, and then you hear the louvers close or open, and you can, oh, yep, it's 60 whatever degrees the set point is, depending on which way it's going. But what was amazing in this was there was just a lot of analysis trying to figure out where we're going to be able to reach comfort conditions with the natural component in the system. And so we actually had the engineers do a lot of runs to validate that we'd actually be able to meet that without having to completely close that space off. This was the stormwater structure that Gary alluded to. So that Skip Metzger, who I think spoke to you guys earlier, took these photos after one of the big rains a year or two ago, and I thought it just captured what it's supposed to do exactly. So you have the roof water coming off, hitting these splash blocks, and then it goes through a series of weirs along this infiltration channel, and then overflows into this small detention thing, which then overflows into the storm system. And so very rarely in a rain event do you actually see that overflowing unless we're having some pretty significant rainfall. So it's actually gotten, it's funny on the drawings, it looked kind of interesting, but you didn't really get a sense of its physical presence. But now, going out there in the rain, it's just a dramatic feature. People have really responded nicely to it. This is the Tahoe Center, or this picture kind of looks like the Tahoe Resort and Casino. We've got an education center in it that's got some really nice features. If you guys have a chance to get up there, it's a wonderful education center that's got some self-guided tours and docent-led tours. But because this is an environmental program, we had some real high goals for sustainability. It was an extremely challenging project because it was a joint venture with a private Nevada institution working with us. But again, some photos. We had this building went for and achieved LEED Platinum. We did get a donor committing. We were pretty much at the end of the design, and a donor came in and said, "How much would it take to go to platinum?" And we just said sort of $1 million, and thinking that would make them go away. And they said, "Okay." So sort of call our bluff, and we had to put the PVs in and stuff. Like Gary said, some of those things certainly drove the cost. So it's got a cogen unit where you generate electricity on site and then capture the waste heat to heat the building. It's got pretty advanced lab controls. We designed the basement to actually see all this stuff almost as a tour structure, which is, unfortunately, we don't have a luxury on a lot of our on-campus buildings. You go in there, it's like a submarine. But the idea was that people could see the systems, and we actually came back and color-coded all the pipes. This one also does have a rainwater capture system you see in the top left, so the rain comes off the roof and is used to flush the toilets. If we have time, I'll tell you a little story about that too. Med 3B, again, it's not built yet, so I've got some design things. This is a lab building over in the Health Science District right next to BMIF or Valley Hall. You can see sunshades, a lot of very intensive daylighting design. This was just to give you a sense of some of the analysis that goes into this. So this is actually a computational fluid dynamics where you actually model the heat flow in a space, where we're trying to figure out where the sunshades, the light shelves, and the glazing type all balance out. And so this was interesting because we had optimized the daylighting, and the space looked really good from a daylighting perspective, getting real high light levels. And then the mechanical engineer gave me a call and said, we got to talk, the guy's head's on fire. And you can see the person here in this diagram is sitting here. This is their head, the computer on the desk. And it turned out when optimizing the glass, we'd actually created too much heat in these offices. And so we had to do some additional shading on the outside to reduce that down, and we got it back down to this level. So it's, it's again, like Gary said, it's this constant balancing of multiple variables to try to achieve sort of the best for all. This one, again, is looking at not just a rainwater catchment system, but we're actually capturing a lot of, there's processed water associated with fish culture that go on in this building. And it gets processed back and used to flush the toilets. And this pretty much even, the tanks, we tried to balance it to the process loads, so this doesn't have anywhere near the tank capacity that Julie's winery project does, because this just sits in the mechanical room, so we ended up doing kind of a balance. So back to this graph. So this was an attempt to look, okay, this is where our trajectory is going with energy use on the campus. How do we ever get to the goals? And again, at a relatively high level, we plugged in several different measures. So you can see the A line is essentially, there's a large program going on called the Strategic Energy Partnership that's doing a lot of energy retrofits in existing buildings. And so the A line, you can see if all those are applied at a level of intensity, it's about $25 million of projects. It can create a substantial dip in that line, but it still doesn't get to even the first goal of 2014. So then I applied, if we did more intensive measures, which involved users, so it involved people like turning off the lights more, trading in their laser printer for a more energy efficient model, things that really kind of people have more individual control on, and it got a nice dip below that. And then the third one was a $25 million in a plasma plant, which the technology is still pretty questionable, but essentially it's a waste energy where you take your waste stream, all the waste coming from campus, and you actually burn it in a plasma arc, and it generates a synthetic gas. And that created an equivalent kind of drop almost compared to B. Again, these are all cumulative. Once you do these, you can go. And then I also looked at a solar investment of about the same amount. So these are essentially like $25 million steps. And then the last one was just slowing the growth rate of additional construction by half. So essentially, we built. Now this was done in 2007, so the economy has sort of done a little bit of this for us with the state budget. But you can see it takes all those measures cumulatively to even get to the 2020 goal, and we just make it about there. And again, this is at a relatively high level, but it's just trying to bracket that issue. So, so then the next part of the campus commitment is climate neutrality. So you've done all this stuff, so the question is, how do you get that to keep going down with the building stuff? So here's just some options just to throw out for discussion. So one thing would be to say, okay, we're not going to build any new buildings at all. We just stop construction. I'll probably finish what's being built, but basically just shut that down and say, okay, we're going to flatline growth. So what would it take to do that? You'd have to significantly increase the intensification of use. I mean, you'd have to, instead of classes running a certain time of day, you would have to see classes, actually this has to do with more the schedule component. Program space would be more like, okay, now office space for people has to get smaller, people have to fit more people into office space, just a real, essentially people are going to have to be a little bit more conscientious about how much space they use in their program. The second part would be schedule, that you'd have to, okay, now we're going to have classes that run till midnight every day, or it's going to run through the weekend. That kind of overlap. And then the other one actually is renovating space that's being used at relatively light usage levels. Like, for example, there's a lot of buildings that have large offices, and obviously it's too cost ineffective to go in through and remodel that whole building to change those offices unless you were trying to achieve something like this, where you're really trying to bring a lot more people in. The other one that's a little counterintuitive is we have about 500, depending on which numbers you look at, it's between 300 and 400,000 of off-campus lease space in Davis, which are typically in developer buildings that are running just barely at code. I mean, they're designed, I mean, that's how developers optimize, is typically put them right at code. So if we brought them back into so they're creating a greenhouse gas profile that's significantly larger than an equivalent apartment on campus. Another idea is that capital projects have to come with essentially their own mitigation plan. So I did just a quick run. If we took it's kind of a standard university office and classroom building, 100,000 square feet, $45 million of the project cost, to just offset the CO2 that goes into the construction, this would be commercial. This is essentially a sort of a high-quality carbon credit offset that you could buy on the market now that would meet European Union standards. So it's about $60,000 just to say, okay, you can go ahead with construction. We've neutralized the emissions associated with that construction. Once you go to the operating energy, there's a solar project going on now, and this is numbers based on that, which is if you were just going to pay the premium difference between what campus pays now to go to all green power, it'd be about $150,000 a year for a project like this. So essentially that building every year would have to pay that amount of premium in order to sort of neutralize its operating energy. And the other alternative would be for one time of about $350,000 to invest in other energy efficiency measures on campus. And then one other thing, a little smaller scale, would be to try to get departments a portion of savings that they could actually drive. In other words, if a department had control, enough input to be able to say, okay, if we work with everybody in our department to reduce energy by this much, can we get some benefit back from that? So the campus gets the bulk, the department gets to keep a portion of that.
Is there a question?
Sure.
When you were showing on the slide where you were rationing it down, what percentage were you assuming that the user level was actually attaining? And what made you, do you actually think that's a $25 million investment? So, two questions.
What percentage did I think the user?
Yeah, how much is that dropping? It's
I don't know that. It depends on which year, and
yeah.
how that applies. But
So you're seeing it increase over time.
This was the 25 million in that case was a little different because I applied it in a couple batches in order to keep it. Because if you just did it as, okay, we're going to do this huge outreach program and get everybody to turn off the lights, you'd see that climb faster and it would actually start to approach this line. So I actually had parsed that out over, so it's like, I think it's like 5 million in a couple different increments. But that one was a bigger wag than the other ones just because, how do you price a user program like that, But it was considering, rebates for refrigerators,
Printers.
copiers, printers, stuff like that. In terms, does that get to both your question?
Well, I'm still wondering on the total percentage that you achieved with that, whether or not, maybe, anyway, we can talk about it.
I can give you detail. So this was just, again, some more food for thought. So if we put, because a lot of times people think, okay, we're going to save it, we're going to reduce the energy down, and then we'll just buy PVs or that we can put around the campus, and we'll make it up that way to achieve neutrality. So if we covered every roof on every building on the central campus with PVs, we could generate about 8% of the current load. If we wanted to pick up the whole load, this would be the area of solar panels that you would need. So we'd have to think about, do you get rid of the whole agricultural research program, because it essentially covers all the ag fields. And then I was just thinking aesthetically, what does that feel like to have a huge structure that's essentially covering the ground that then goes fallow? So again, just to get to bracket this problem. And then obviously there's other alternatives like remote solar thermal or wind farms that could be punched to campus. So you want to start the discussion?
So, we were trying to think of an analogy of kind of where we're at as a campus, maybe as a country. And the one we came up with may not be the best one, but the analogy we came up with was somebody who is approaching retirement, let's say about 60 years old. And let's say a few years ago, that person started saving $100 a month towards retirement. And at age 60, they realized that's not going to quite make it. They don't have a pension plan, that's their, besides Social Security, that's the only way they're going to retire. So what they do, they say, well, let's double that. I'll save $200 a month. So on one hand, that's great. That's 100% improvement on what they've been doing. But if they did the math, they would realize that by the time they're 65, that would yield enough income to maybe live for about 4 months of retirement. It's just not even anywhere near what they need to do to get where they're going. Well, I think the Regions policy, the LEAD program, and a lot of sustainability is very analogous to that. We've recognized a need to make improvements. We are starting to make improvements. They're not that easy to make, actually, in many cases. But we haven't really thought about, well, how many improvements, where do we really need to go to achieve sustainability? And I think people who have looked at it have concluded that we are very, very, very far from getting there. The buildings that we showed you today, I think we're very proud of in many respects, but they aren't even close to being sustainable. They're just simply less unsustainable than they would otherwise be. So the question is, well, what even is sustainability? You know, what would be fully sustainable? How do you even define that? And a lot of people have tried, and there are various different definitions of that. So it's just a question. I don't have the answer.
This is where we go to discussion.
Yeah, we're going to go to discussion. Very few, if any, institutions that we know of have even attempted to set full sustainability as a goal. They've just done things like the Regions have, which is admirable. We're going to move towards sustainability, but we're not even going to try to go to full sustainability. And the reason we're trying to define that and get there. So, you know, the questions we have is, you know, well, how would you define it? What would the university look like, you know, in a sustainable scenario? There's probably a lot of different scenarios. And how, you know, how does that goal conflict or enhance our basic mission, which is by charter, state charter, education, research, and public service? A lot of the reasons why our buildings, for example, are not more sustainable than they are is because faculty and administration and the regions feel that that conflicts with other goals. And when we have a fixed budget to build a building and a chair of department wants as much space as possible to meet their program, that conflicts with the need to make that building more energy efficient and invest in the systems that are needed to do that. So there's a real tension there. On the other hand, I think that going towards sustainability clearly is very compatible with our mission of education, research, and public service. So there's tension there. And then sort of lastly, the question is, well, you know, what would we need to do? How would we even initiate that dialogue? How would we reach a consensus? How would we get the resources we need to go there? So those are some of the things that we've been thinking about, don't have any answers to.
A similar thing along that we actually had kind of preparing for this a conversation started where we were saying, well, you know, in order to get there, does the university have any sort of, do we essentially get a free pass by saying, you know, we're doing so many good things that we can use up more resources than other people can? And I mean, that's sort of how taxes work, right? I mean, we're distributing, people are paying taxes so that we can do work that we think is important. You know, on the other hand, we have some of the we have greater benefits than anybody else has. I mean, we have a campus with all our own utilities that we can make decisions about that. You know, we've got people that are typically living in close proximity. So we have all these, you know, things that you would say, these were all the foundational aspects you need to make a truly sustainable community. So we were trying to figure out, you know, do you actually get get let off the hook, or do you actually have more responsibility to get to this goal earlier than other people? So I'd love to hear anybody's thoughts or questions.
There are also some really fundamental philosophical questions I think you have to answer before you can even talk about the bioengineering and the details. There was a book written a few years ago by somebody named Jim Merkel called Radical Simplicity, where he actually attempted to figure out what it would take to actually become sustainable, fully sustainable, just in his own personal life. And the first things he had to grapple with before he could even begin to answer that on a technical level were pretty deep philosophical questions like social equity. You know, is it okay for me as a North American to consume 100 times more than somebody living in Bangladesh or twice as much as someone living in Western Europe? If you say yes, that yields one set of metrics. If you say no, everybody should live at a level that's equally sustainable. If everybody lived at that level, the world could be sustainable. That's a very different metric. Another metric is species equity, if you want to call it that. You know, how much of the bioproductive area of the earth do we reserve for other species? Or do we say every square inch of it will be reserved for human beings? And, you know, resulting in the mass extinction that's going on right now.
You can kind of see we have trouble keeping it limited to green buildings.
Yeah. Right, so, I mean, there's pretty fundamental. And then maybe a last big one is, well, how many people do we need to provide for? Again, depending on your answer to that question, you know, are we going to allow the population to keep growing? Well, that comes into the equation. Are we going to cap it where it's at? Or are we going to say, no, we're going to drive it down or let it gradually reduce down? Again, that yields a very different set of metrics about, you know, how you use water resources, land resources, and other resources. So,
Anybody have a vision of what they think the university would look like?
I do. It would be underground completely, or primarily, which takes away all your mechanical heating and cooling. It would recycle surface water as you're doing. The cistern idea is cute. It worked well in the 19th century where every building had a cistern. The scale of them now is much better. McDonough and others show bioremediation and 100-foot of waterfall you can clean up most of the water in any building if you don't go a mechanical way. I see that the percentage of leads now that has fallen to the Sustainable Sites initiative is now almost 30%. We're landscape architects. We've been doing this for 2,000 years. We know how to make sustainable communities. We're probably not getting our word out. And you guys have known how to make buildings for at least 2,000 years that are sustainable. I mean, they're all over the world. They're clear. I just think that the vision for the future is really to look sort of to the past. The one real problem is that it's probably what Paolo Soleri says, and it's true, that the density is way too low, and even in our high-rise buildings, you got to go down, go out, and go up another building, and all the entropy of the sides and everything, where he builds megastructures, which the advantages from energy, it's like any computer chip. You don't have to go too far, you're not expending energy, and there's not a whole lot of entropy in the system. Those are really radical ideas, but certainly the underground issue for California, we're sitting on hundreds of feet of moldable soils. The water is already there, 10-foot water table. I don't think on this campus we're really even looking at those kind of alternatives that I've seen. I would hope
very few buildings with basements.
Hope you guys would take us that way.
Well, I'll just throw one more thing out before we wrap up that. We were talking also about, you know, with the issue of like solar, a lot of times you'll have engineering solutions come back and says, well, we should put it on over all the parking. And you know, one of the things is, how does that feel? I mean, you know, it's like parking lots aren't particularly great environments to begin with, and they're typically made better by planting but at least in our traditional sense, but if you cover them all with PVs, is that an acceptable solution to the majority of people, you know, or do people need a balancing? So that's, I think there's a lot of areas sometimes where these things get thrown out as a number, and then there's another step of visualizing, is that acceptable to people as an environment that they actually want to inhabit? And I guess I would pose that to the underground situation as well, you know.
Question back there?
Are there other types of renewable energy that you're considering, and also at the rate at which PV is increasing in efficiency, do you foresee, you know, maybe in the future that 8% capacity due to efficiency increases could rise to something more reasonable that would cover a greater portion? So maybe just wait for the technology to come around before implementing.
Yeah. Just to give you a little bit of scale, that's using the best panels that you can get right now and the highest production rate that you can get in terms of hours. So I haven't seen any estimates that you're going to see the same kind of like improvements like you have in computer, you know, memory and stuff like that. But there's obviously going to be continued efficiency gains. But it starts to get like, you know, when do you buy the most efficient computer?
Yeah.
You know, I mean, it's always moving up, but at some point.
And the question of other renewables?
What's that?
Other renewables?
The plasma arc was one that was, you know, some money was spent kind of looking into that, and I think at this point, I'm not aware of the campus looking at other stuff besides, I think there's one other one that I know that Alan Doyle's been mentioning. Do you remember the name of that one? It's again, another gasification process using waste, but it's an oxidation-based process and not a combustion, not a typical combustion-based process. So,
Well, we're looking at a biodigester for West Village, but then that begs the question of what do you have left? If you're using, how much feedstock are you shipping to that, and then how much feedstock is left, and would that then make plasma actually really doable, or would you need to go outside of your boundaries to find your feedstock? How would that work?
that actually came up. I know that our engineering director was looking into the plasma arc, and it uses a waste stream, waste to generate energy. And so he was calling around a couple locales and called West Sacramento. And in our calculation, we were figuring we'd be able to get waste from other sources to be able to run it at full productivity. And so he called West Sacramento and was asking the guy, "Are you looking into a plasma arc reactor too?" And the guy was real cagey about it. And finally, on pressing, found out that when they were doing their analysis, they were planning on using our waste to arrive at it. And so as you start looking at these, everybody's assuming that they're going to be able to utilize all these other resources, you know, because they think it has no value at that time. Well, it changes the equation pretty quickly if you start looking at, you know, digestion. So right now, there's plans. Oh, if that was using all the compostable waste as well, what does the student farm do? Because they rely on a compost stream, you know. So that's interesting when you start looking at that, how you have to start asking around, making sure you're not taking away from somebody else at the same time you think it's just generating. Okay.
Bill and Jerry, thank you very much. Willing to stick out for a minute, 5 minutes?